Hello everybody. In this video I'm going to show you how to find out the center of gravity or centroid of any mass. Okay, so first of all we need to know what is center of gravity. If you take any mass, then basically there are millions of particles inside it, right? And each of them has a small weight there, means like, and this one is working towards the center of the earth because of the gravity, right? So the weight of that mass is basically nothing but the summation of all the weight for individual particle, and if you get the total or resultant, that's actually the weight of that mass. Now you can understand that this resultant force is working at a single point of that mass. So if you take the moment of all the particles there, and if you take the resultant moment of the resultant force, then basically they has to be equal, right? So there will be a single point in that any mass where the resultant is passing through, right? That's actually the center of gravity or the centroid. For example, let me take this book here, and you can see there are millions of particles here, and all the particles has their own weight, which is working towards the center of the earth, and the resultant weight or the total weight of this book is actually the resultant or the arithmetical summation of all the weight for each of the particles, right? Now there is a single point here, like where the centroid or the center of gravity, if I can look at that one, then basically this one be in a equilibrium position, right? So basically we have to find out the center of gravity, and if I put like my finger correctly, then basically this one will be in equilibrium. But anyway, I can't find that out by myself. I'm not a magician. You can try that one, okay? But mathematically, we'll be able to find that one. Now, let's try to see here that how we can develop the mathematical formula to find out the centroid of a mass, okay? So, let's say in this figure, there are multiple, like particles here, and the total weight is W, which is actually the location of that point is actually X bar, Y bar, and Z bar. X bar, Y bar, and Z bar is actually the center of gravity of the total mass, okay? Now I take a very small, like weight here, which is dW, working at that location, and the location of this one is X quiggly bar, Y quiggly bar, and Z quiggly bar, okay? That's the location of that infinitely small weight here, okay? Now you can understand that your total weight is nothing but integration of dW, right? That's the first thing. Now, what we can do, we can take a moment at x-axis or y-axis and then try to see the moment of the resultant has to be equal to the moment, summation of moment of all the particles there, right? So let's take a moment here, summation of moment along y-axis. That has to be 0. So you can see actually your W into X bar, that has to be like this, okay? So you can see that's the summation of all the single like small weight here. Now if I try to find out X bar, that's basically X quiggly bar dW divided by W, which is actually nothing but integration of dW. okay? Similarly, if I take a moment along the y-axis, then I can find out my y bar, which is actually integration of y Quigley-Bar dw divided by integration of dw. In many cases, actually, we see when the thickness is uniform or constant throughout the cross section, then basically we can find out the centroid of an area, which is actually same as the center of gravity. So in that situation, actually, your x bar would be dA divided by integration of dA. Similarly, your y bar is equal to y Quigley-Bar dA divided by integration of dA. Now, if you think about a line here, okay, and you want to find out what is the centroid of that line, then basically your x bar has to be x Quigley-Bar dl. dl is the small length divided by dl. Okay, that's the formula we are going to use the first part of this chapter. Okay, now let's try to see that how we can use that formula to find out the centroid or center of gravity for different structures. Okay, let's move forward. So problem number 9-9 is saying that locate the centroid x bar of the shaded area. So this is by shaded area. You have to find out the x bar of this shaded area. Okay, so basically to do that, we have to take a very small area here. Let's say I just take a very small area here. So the thickness of this one is, let's say, dy. And you can understand that dy is very, very small, right? And this point here is, let's say, xy. So when this one is very, very small, like this thickness, then basically this one is just like a line here. So what would be the center of that line? We already know that the center of a line would be at the midpoint, or center of a triangle is also at the midpoint, right? So here is the centroid of that midpoint, and you can remember that this is actually your x Quigley-Bar. Okay, so if I try to show that one here, then basically first of all you see your dA is equal to x into dy, right? And you can also see your x Quigley-Bar, that is actually x by 2. So this is x, and the centroid of this small element is basically the half of x here. Okay, so you have to remember that one, that x Quigley-Bar is the centroid of that small area. Okay, and x bar is the centroid of the whole area. Okay, so now you can see we already have the equation here, that y equal to 1/4 of x squared. So x is equal to 2y to the power half. right? Now, if I write my equation, then I know that x bar is equal to integration of x squiggly bar dA integration of dA, right? So if I plug that value x bar, which is actually x by 2, but x is equal to, let me write the whole thing first. So x by 2, so that actually y to the power half, and dA equal to x into dy, so that's actually 2 and dA here is x dy, so that's actually 2 and dy can vary from 0 to 4, right? From 0 to 4. So if I simplify that one here, that you can say 2y dy, and this is 2y to the power half. So that y squared by 2, and this is 2/3 of y to the power 3 by 2, and this is from 0 to 4. So if you plug the value here, that actually you will get 3 by 2 meter. Okay? So that's your answer, 3 by 2 meter or 1.5 meter. Now, they didn't ask here like for 9-9, but for 9-10, they actually ask you to find out the y bar here. Okay? The y bar here. Now for y bar, you can see here that the centroid of that small thing here, that's actually your y squiggly bar. So now you can see that's actually same as y, right? Now if I say what is my dA, that remains same. So that actually x dy, right? And your y squiggly bar is equal to y here. Okay? So now we know our y bar is equal to y squiggly bar dA divided by d. Okay? So if I plug that value, that's actually y, and then you can see dA is x dy, and this one is x dy. And again we see that x equal to 2y to the power half. So if I plug that value here, so y into 2y to the power half and x equal to 2y to the power half and your dy varies from 0 to 4. So this one is y 3 by 2 divided by y half. So if you integrate that one here, that would be 2/5 of y to the power 5 by 2 and 2/3 of y to the power 3 by 2. That's basically 12 by 5 meter. Okay, that's the way you can find out the y bar here too. Now let's move forward. Problem number 9-28. Okay, this is the figure of this problem, and they're saying that find out the centroid x bar of the shaded area. This is your shaded area. Okay, you have to find out the x bar here. So what we do here, we just take a small area here. Let's say this is x1, y1, and this is x2, y2. So the centroid here of that small area, or x squiggly, that's actually because x1 and y1 is actually same point because they are vertical here, right? So x, I can see this is xy1 and this is xy2 here. So the distance from here to here, that would be y2 minus y1. So what is the area dA? y2 minus y1 into dx. That's actually very small width here. Dx. So dA is equal to y2 minus y1 into dx. Now what is y2? You can see in this equation y is equal to x minus y1. So y is 1/100 of x squared. So that's your dA. Okay, now we know x bar is equal to x squiggly bar dA divided by integration of dA. Okay, so you can see here actually x squiggly bar is actually x here, right? You can see the centroid of that small area is actually the same from here to here because this is x here, right? So if I just try to plug that value here, so you will see integration of x into x minus x squared by 100 dx, and this one is x minus x squared by 100 dx. And you can see your dx can vary from 0 to 100 millimeter, right? So this one would be x squared minus x cubed by 100 So if you integrate that one, that would be x cubed by 3 minus x to the power 4 by 400 divided by x squared by 2 minus x cubed by 300. So if you plug that value, actually you will get this one is 50 millimeter. Okay, let's move forward. Now we are going to discuss about composite body or composite loading. Okay, so composite loading or composite body means like actually this is kind of like consists of some regular shape, rectangle, square, or semicircle, circle, that kind of shape here. So we know the actual area of that simple shape, so we can avoid integration in that case and find out the centroid of this composite shape. Okay, actually you will see in practical life this is the most common one you will see most of the time. Okay, so we need to learn that one quite well. For example, you can see here that this is a kind of composite loading here. Okay, so for that loading I'm assuming this is the weight W1, and this W1 is working at a distance at the centroid of this area, which is squiggly x1. Now I have another rectangle here, and this force is the resultant force of this one is working, which is W2, and which is working at a distance squiggly x2. Similarly, this is a triangular loading, and the weight of this one is W3, which is working at a distance x squiggly 3 from there. Okay, now if I say, hey, what's the total or resultant force working here, that's actually W. So W is basically nothing but W1 plus W2 plus W3, right? Because all of them are parallel force working downward. Now what is the location of that resultant force? Let's say this is actually your resultant force is your x bar. Okay, that's the centroid. So if you take a moment along the y-axis, so then you can see actually x bar multiplied by W that should be equal to W1 x squiggly 1 plus W2 x squiggly 2 plus W3 x squiggly 3. So your x bar would be basically summation of n equal to 1 to n wi x squiggly I divided by w, which is actually summation of okay. So if you have 3 elements, then basically your x bar would be w1 x squiggly 1 plus w2 into x squiggly 2 plus w3 into x squiggly 3 divided by w1 plus w2 plus w3. Okay, and similarly your y bar would be okay. The only change is like x would be here is not x squiggly bar, but that would be y squiggly bar. Okay, so that's the way we have to solve the problem. First of all, we have to just take a look, like in your composite body, that how many, I can combine that one with how many regular shape. And for each of the regular shape, actually the location of the centroid is known. So basically I'll be able to find out the x bar and y bar of the composite body using this equation here. Okay, now let's see some of the example here. Okay, problem number 9-62. Okay, here is the figure. You can see they are talking about this area here, that find out the, let's say, x and y bar for this area here. Okay, now first of all we have to see that how many regular shape we can like make from this composite body. Okay, so you can see you can take this one plus this one and then this one, 3, right? You can do that one different ways though, that's your freedom, but always try to find out the area which is actually as minimum as possible. Okay, regular shape, but try to make that one minimum, as minimum number you can do that. So for here, let's say this is area 1. Let's say I'll just divide that one like this. So this is a square area and this is a triangular area. So I have 3 segments or 3 components. Okay, now at the beginning I'll just try to say you like just try to make a table like that. Once you will be more familiar, then basically you don't need that table anymore. Okay, but at the beginning that would be very, very helpful. So let's say start with segment 1. So what's the area of that segment here? 1. You can see half into 6 into 9. So that's actually that's 27, right? What is the x bar? And the x squiggly bar for this area. So this is my y-axis. I have to measure everything from here. So I can see this is the apex, which is 6 inches from here to here. So that would be actually 1/3 from the base and 2/3 from the apex. So I see the centroid is somewhere here. That's actually your, which is actually 2" here. Okay, now if you see like, oh well, I can do this part here too. You can see the centroid measured from here. This is your x-axis, so you can see this one is actually total 9, so this one has to be 6 from the apex, right? Now I can calculate that one later on, but let's try to see like segment 2. So what's the area of that segment? That's 6 into 6 is equal to 36. Okay, so what's the centroid of this one? It's 6 and 6. So if you measure from here to here, that's actually -3. And you can see this one is y is 3 here, right? The centroid is somewhere here, which is 3 from here and -3 from here. Why minus? Because I'm measuring that one in the other side of the y-axis. Okay, so I can do this one later on. And then number 3 here, you can see this one is half into 3 into 6. That's actually 9. So that's basically your summation of area, total area, right? 27 plus 36 plus, that's actually 72. Now you can see when I said like this is my Quigley bar multiplied by area, so this into this, so that's actually 27 into 2, that's actually 54, right? Similarly, if you do this multiplied by this, so that would be 36 into -3, that would be -108. And then, oh, I didn't do this part here. So you can see the x Quigley bar for this one, okay, for 3 is actually from here to here, 1/3 of the base. So total is 6, so from here that would be 1/3 means like 2. So that's actually -2 here, right? Because this is the other side. Now, what about the y bar here? You can see from here to here is 6, and from here to here that has to be 1, right? Because this is base and this is apex. So this is 3, so 1/3 of 3 is 1, so 6 plus 1, that's actually 7, okay? Let me repeat that one more time, right? So you can see for this one, you are measuring everything from x-axis. So from here to here is 6. Now you try to see that from here to here, how far is that? So total is 3, and this is your base, this is your apex, so it's 1/3 from the base. So 1/3 of 3 is actually 1. So 6 plus 1, that's actually 7 here, okay? So I can write that one here. That would be 2 into 9. Okay, similarly I can fill that one here. That's basically this into this. This one is 36 into 3, and this one is 9 into 7. So you can just find out this is your summation of x squiggly bar A, and this is your summation of y squiggly bar A. So if you add them, then basically you get this one is minus 72, and this one is 333. Okay, so we know our x bar is equal to summation of x squiggly bar A divided by A, or summation of A. Okay, so it means like this divided by this. So that's actually minus 72 divided by 72. That's actually 1h. Okay, the centroid of the actually -1 here. So centroid of the composite has to be somewhere here. Okay. -1. Now you can find out your y bar, which is basically summation of y squiggly bar A divided by summation of A. So that's 333 divided by 72. That's actually 4.625. Okay, so your y bar is actually here, which is 4.625 inch. Okay, let's move forward. Problem number 9-64. Okay, so this is the figure here, and they're asking you to find the centroid of this composite body. Okay, and you can see there is actually a gap here. Okay, so first of all you have to decide that how many segments you are gonna consider here. Okay, that's up to your freedom, but I see that this one would be good, like if I take like this one, number 1, number 2, number 3, minus this area. Okay, this area, because there is an open area here. So my total area here, area would be equal to A1 plus A2 plus A3 minus A4. Okay, now one of the most important things here, that how far is the y squiggly 4 from for this one, you know, like this is a half circle, this is a quarter circle. Okay, to find that out, actually if you see the last page of your book, let me show that one here. This is the last page of your book. Okay, you can see here that this is quarter circle and this is half circle, and they gave you the location of the centroid for these regular areas. So that's actually here, the distance here is 4r by 3 pi. Similarly here, this one is also 4r by 3 pi, and this is 4r by 3 pi. Okay, now we can just start working on that. So basically my x bar would be equal to x prime x squiggly bar A1 plus x2 quickly bar A2 plus x3 quickly bar A3 minus x quickly bar A4 divided by A1 plus A2 plus A3 minus A4. Okay? So that's the formula. Now I can start putting that one here, that all the values. If you want to make a table at the beginning, like that would be very helpful. If you don't want to make a table and do that one a little bit faster, then basically you just put that like formula here and try to put the values here. Okay, so here this one has to be x quickly bar for x1 quickly bar and A1. So this is my segment A, and I said the x bar is 4r by 3 pi, right? So 4r by 3 pi. So 4r is actually 3 inch. Then you can multiply that one A1, which is pi r square, which is 3 by 4, right? This is 1/4 of a circle. So pi r square divided by 4. So that's the first part, and then go to the second part, was the x quickly bar 2. That's basically from here to here, which is definitely 1.5 negative, because this is the other side of that thing, okay? So negative 1.5 multiplied by the area of this one, which is actually 3 into 3, okay, plus for the third one, you can see the distance from here to here is 3 plus 1, okay, because total is 3. This is apex, this is the base, so this is 2/3 from here, so this is 2 and this is 1. So the total is actually 3 plus 1, so 4 multiplied by the area, which is half into 3 into 3, minus this one here. So here you can see x bar is basically 0 here, because this is symmetric, this side and that side, right? So the x bar is basically, x quickly bar is basically 0. So I can just see 0 into pi 1 square by 2. That divided by the area, and the area is pi r square by 4. Actually this term, this term, this term, and this term, right? This, then this one becomes actually 9 plus 4.5 minus this part here, pi divided by 2, because 1 square is equal to 1, okay? So if you solve that one, that would be actually minus 1.18. Oh, I made a mistake here. This one has to be negative here, okay? This one has to be negative because I'm measuring that one from here to here, okay? And this one is gonna go to 0. Now let's try to do that one for y bar. So for y bar, actually the only thing this one is going to change is y1, y2, y3, y4, and then a1 plus a2 plus a3 minus a4. Okay, that's the formula here. Okay, now I start writing that one here. You can see for this one, the distance, like y quickly bar 1 is equal to 4r by 3 pi. So r equal to 3. Then the area, which is pi 3 squared divided by 4. Okay, then plus y2 quickly bar. So y2 is actually, y2 quickly bar is from here to here, which is half of 3. So 1.5 multiplied by the area A2, which is 3 into 3, total 9 here, plus for this one you can see the y quickly bar, that has to total 3, and this is apex and this is the base, so 1/3 from the base, that's actually 1, and the area is half into 3 into 3 minus y quickly bar is 4 into 1 divided by 3 pi, and the area of this one is pi 1 square by 2. Okay, divided by the area a1 plus a2 plus a3 minus a4, so pi 3 squared divided by 4 plus 9 plus half into 3 into 3 minus pi by 2. Okay, so this one is basically 1.39 inch. So for this composite area, so this one has to be somewhere here. That's your x bar. What we got is 1.18, and this is your y bar, which is actually 1.39 inch. Okay, thank you for watching.